afternoon to all of you. First of all, I want to introduce myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering, and today my content is GTU question paper solution of the subject of vector calculus and linear algebra of January 2013. So up to question number 3 we already seen this question paper. So let's see, start question number 4. Question number 4a. Let capital A is equal to this 2 cross 2 matrix A1, A2, A3, A4, and capital B is equal to B1, B2, B3, B4, B2 matrices in real matrix space M 2 cross 2, and let this inner product AB, that is equal to A1, B1 plus A2, B2 plus A3, B3 plus A4, B4. Show that this notation, this inner product AB is an inner product in set of 2 cross 2 matrix, right? Now we want to prove that this is inner product, right? This operation is an inner product that we have to prove, and for that we have to prove 4 conditions. First of all, the first condition is we have to prove inner product AB, that is equal to inner product BA, then inner product K A B, that is equal to K inner product AB, right? Then so this third property, then inner product A plus B C, that is equal to inner product AC plus inner product BC, and then inner product A with A, that is always greater or equal to 0, and if inner product A with A, that is equal to 0, then we have to prove that capital A is equal to 0 matrix, right? So let's start one by one each conditions, each exams we have to prove. Let's see, already A and B, capital A and B already given in the example, right? So A1, A2, A3, A4, and capital B is B1, B2, B3, B4. Let C is equal to in matrix C1, C2, C3, C4 belongs to set of 2 cross 2 matrix, and let alpha belongs to R, right? So inner product AB, that is equal to A1, B1 plus A2, B2 plus A3, B3 plus A4, B4, that is equal to B1, A1 plus B2, A2 plus B3, A3 plus B4, A4, that is equal to inner product BA. Okay, so inner product AB is equal to inner product BA. Now next is next condition, we want to prove inner product A plus BC, that is equal to inner product AC plus inner product BC. So A plus B is equal to A1, A2, A3, A4 plus B1, B2, B3, B4, that is equal to A1 plus B1, A2 plus B2, A3 plus B3, A4 plus B4. So A plus B, inner product A plus BC, that is equal to A1 plus B1 into C1 plus A2 plus B2 into C2 plus A3 plus B3 into C3 plus A4 plus B4 into C4. So that is equal to A1 C1 plus A2 C2 plus A3 C3 plus A4 C4 plus in bracket you can see just a simplification when we leave this bracket, leave this all bracket, we can easily get this step. So B1 C1 plus B2 C2 plus B3 C3 plus B4 C4. Now the first bracket is exactly inner product AC, right, using the definition which is already given in the statement, and the second bracket is inner product BC. So we prove that inner product A plus BC, that is equal to inner product AC plus inner product BC. Now third property is alpha A. Now A is A1, A2, A3, A4. So alpha A, that is equal to alpha into A1, A2, A3, A4, that is equal to alpha A1, alpha A2, alpha A3, alpha A4, right? And this is equal to alpha A B, that is equal to alpha A1 B1 plus alpha A2 B2 plus alpha A3 B3 plus alpha A4 B4. that is equal to alpha into a1 b1 plus a2 b2 plus a3 b3 plus a4 b4, that is equal to alpha into inner product AB. Okay, so inner product, we prove that inner product alpha A B, that is equal to alpha inner product AB, right? That we prove. Now next property, we want to prove that inner product A with A, that is equal to a1 square plus a2 square plus a3 square plus a4 square, right? Because you can see inner product AB, how we define inner product AB? A is equal to a1 a2 a3 a4, B is equal to b1 b2 b3 b4. So inner product AB, which we define like a1 b1, right? First coordinate, multiplication of first coordinate in both of the matrix, then multiplication of the second coordinate, then the third coordinate, this is the third one, right? a3 b3 and a4 b4. So now when we define inner product A with A, so that means what? A1 a2 a3 a4, and again we have the same matrix a1 a2 a3 a4. So when we define inner product A with A, that is equal to a1 into a1 plus a2 into a2 plus a3 into a3 plus a4 into a4. So definitely you will get that is equal to a1 square plus a2 square plus a3 square plus a4 square, right? And that is always greater or equal to 0. Inner product A with A, that is always greater or equal to 0. Okay, now next we want to prove that if inner product A with A, that is equal to 0, then we have to prove that capital A, that the matrix is a 0 matrix, that we want to prove. So if inner product A with A is equal to 0, that means what? a1 square plus a2 square plus a3 square plus a4 square, that is equal to 0, right? Now sum of the square of this 4 element equal to 0, that means what? a1 equal to 0, a2 equal to 0, a3 is equal to 0 and a4 is equal to 0. So thus all exams are satisfied for inner product AB. Hence inner product AB is an inner product in set of 2 cross 2 matrix. So this notation, right, that is inner product in set of 2 cross 2 matrix. Okay, and this question was asked in 4 marks in this question paper. Next question 4b. Find the basis for the orthogonal complement of a vector subspace V, where V is equal to span of v1 v2 v3 v4 of vector space R5, where v1 is equal to this vector 2 2 minus 1 0 1, v2 is equal to minus 1 2 minus 3 1, v3 is equal to 1 1 minus 2 0 minus 1, and v4 is equal to 0 0 1 1 1, right? Now first of all, just try to understand the question properly. Find the basis for orthogonal complement of vector space V. Now we want to find orthogonal complement of this vector space, where this vector space is a span of v1 v2 v3 v4, and these 4 vectors are vectors of R5, right? Now there is one important theorem which we can use to solve this example. It says that the orthogonal complement of the matrix A, right, that is exactly the null space, that is exactly the null space of that matrix. Okay, so we convert these 4 vectors in a matrix, right? The space W spanned by v1 v2 v3 v4 is the same as the row space of the matrix. Okay, so we define a matrix A such that the first row is exactly the vector v1, the second row is v2, the third row is v3, and the fourth row is v4. You can see, right? Now we want to find the null space of this matrix. Okay, and for that definitely we have to convert this matrix into a row echelon form. Okay, now what is the meaning of row echelon form or reduced row echelon form? That you should know. Okay, that is a basic portion of to understand the linear system, to solve the linear system of equations and all that. We use augmented matrix, and that augmented matrix we are converting row echelon form or reduced row echelon form. I already sometime told you that what is the meaning of row echelon, reduced row echelon, but I again repeat the meaning of row echelon and reduced row echelon. The row echelon matrix means it satisfied the three conditions. The first one is if there is any zero row, it should be the bottom of the matrix, right? That is the first condition. Now the second condition is below the leading entry or below the pivot, right? Leading entry or pivot means pick up any row and the first non-zero element, that is your leading entry, okay, or sometimes we call pivot. So below that leading entry, in that particular column, all the elements should be 0, right? And the third condition is whenever we are going from above to below, our leading entry is going from left to right, okay. In a matrix, whenever we are going from above to below, our leading entry is going from left to right as a row wise, right? Okay, so if these three conditions are satisfied, then we can say that a matrix is in row echelon form. If there are two more conditions added in these conditions, then we can say that it is a reduced row echelon form matrix, and that two conditions are exactly, the first condition is our leading entry must be 1, right? And the second condition is in that particular column in which leading entry, below that leading entry we have already 0, right? But above that leading entry also we want 0 there. That means what? In any column, if there is any leading entry, then in that column, except the leading entry, all the element must be 0. Either it's below or above, all the element must be 0 in that column if that column have a leading entry, right? So if these two conditions are added, then we can say that our matrix is in reduced row echelon form matrix, okay. So exactly we are converting this matrix into a reduced row echelon form with some row operations, okay. So let's see how we convert this matrix into a row echelon form, right? So here is our matrix. Now here is the first process, R13. We transform the matrix A to its reduced row echelon form as follow. R13, that means we are interchanging first and third row. So you can see first row is now 1 1 minus 2 0 1, and third row is 2 2 minus 1 0 1. Second and fourth row are as it is, that is minus 1 minus 1, 2 minus 3 1, and then 0 0 1 1 1, okay. So now next process is you can see this is our leading entry, right? Below that leading entry we want 0 here, so that's why we multiply first row with 1 and add into the second row, and then multiply first row with minus 2 and add into the third row, okay. So the first row is as it is, 1 1 minus 2 0 minus 1, right? And in fact this is okay, and then minus 1 plus 1 0, minus 1 plus 1 0, then 2 minus 2 again 0, then minus 3 minus 0 minus 3, and this is 1 minus 1, you will get 0 here. Then 2 minus 2 0, then 2 minus 2 0, minus 1 plus 4, so you will get 3, then 0 minus 2 into 0, so you will get 0, and then 1 minus 2, so you will get 3 here, and then the fourth row is as it is, 0 0 1 1 1, okay. Now next process, R24, we are interchanging second and fourth row. So the second row is now 0 0 1 1 1, fourth row is 0 0 0 minus 3 0, first and third row are as it is, 1 1 minus 2 0 minus 1, third row is 0 0 3 0 3, R24. Now the first row is as now next process is we are multiplying second row with 2 and add into the first row, right? and multiplying second row with minus 3 and add into the third row. So here is the process. We are multiplying second row with 2 and add into the first row. So that will become, the first row become now 1 1, then 2 plus minus 2 0, then 2 minus 0 2, and then 1, multiplying second row with 2. So right, so 2 minus 1 1. Okay, so this is now our first new row, 1 1 0 2 0. Second row is as it is, 0 0 1 1 1. Also we are multiplying second row with minus 3 and add into the third row. So the third row become 0 0, then 3 minus 3 0, then 0 minus 3 minus 3, and 3 minus 3 0, and the fourth row is as it is, 0 0 0 minus 3 0. Okay, now the first row and the second row. Now the next process is, we are multiplying third row with minus 1 by 3 and multiplying fourth row with minus 1 by 3. So the third row become 0 0 0 1 0, and the fourth row is also 0 0 0 1 0. The first and second row are as it is, 1 1 0 2 0 0 0 1 1 0. Okay, now next is, we are multiplying third row with 1 and add into the with minus 2 and add into the first row. You can see we are multiplying third row with minus 2 and add into the first row. So all other elements are same, just instead of this 2 you will get 0. Okay, other are same, 1 1 0 0 1, 1 1 0 0 1. Correct. Now next is, we are multiplying third row with minus 1 and add into the second row. So you will get 0 0 1 0 0 0 0 1 0 0, and multiplying third row with minus 1 and add into the fourth row. So you will get 0 0 0 1 0. Okay, see, multiplying third row with minus 1 and add into the fourth row, you will get 0 0 0 0